Okay, so we're going to run through how to enter this Blackbody equation here into Excel and solve for S. So the first thing we did in class was enter in our variables. So we are going to enter in H, which is 6.626, e to the minus 34. So e means power of 10. So this is 6.63 power of 10 minus 34 is what that equals. So if we look at now our next variable, c, speed of light, this is 2.99, whoops, 2.99 e to the 8th. This would be in meters per second. If we look at our third variable, which is k, we have 1.43 e to the negative 23, I believe. Check on that. Yes, minus 23. Whoops. Oops. Try that again. So then we're going to enter in k, 1.34 e to the minus 23. So we have our three constants, h, c, and k. And we're going to put in one of our variables t, which we'll start off with at 10,000 Kelvin. Okay, so what we can then do is define two new variables, or two new constants as a, and a new constant that's related to temperature as b, which is just going to equal 8 pi hc, so that is this term up here. This b is hc divided by kt, which is this term, which reduces our complicated formula into this simplified formula. So if we do, right, to do a formula, we will do equals 8 times pi, so we can enter 3.14 if we wish to do pi, or to do more precisely, you can enter the pi function. So if you do pi, this is a function that defines pi, and if you put brackets, it knows it's pi the number and not pi the two letters as part of a alphanumeric string. So then we are going to multiply that by h. So we do h, and what we're going to do is keep that as a fixed reference. So in that case, we want to do the F4 key, which will put the $ in front of the b and a $ in front of the 2. That way when we pull down the spreadsheet numbers, it always remains fixed at that number. Oops. Back. Try that again. 34. F4. Enter. Then we're going to define B as H F4 times C F4. Oops. Shoot. Go back. Times C F4. So we want this bracketed so that it is taking both numbers and then dividing a new bracket, and we want to divide by KT, so K F4 times temperature F4 bracket. Oops. Screwed up my bracket. Okay. So now we have A and B here, so we're now going to enter in this equation. So what you see is we're going to need now wavelength. So what we're going to do is use these two fixed numbers as a function of temperature and vary wavelength. So we want a bunch of wavelengths that change. So we're going to do this several ways, but we'll do wavelength in nanometers, just because that's something I'm familiar with, and your scales of electromagnetic radiation are in nanometers often. So we'll start with that. So let's start at 10 nanometers, right? And what we're going to do is increment that by 10 nanometers for each cell. So what we'll do is take the cell above and add 10 E and add 10. So what that will do is take the cell above it and add 10 nanometers. So if we pull that down, let's go down, let's go to we'll go to 1,000 just for sport. Alright, so that is our wavelength in nanometers. This equation, of course, we will need it in terms of meters. So if we want to convert nanometers, we just say it's equal to that divided by 1 e to the 9th. So we're converting our nanometers into meters. So some spreadsheets work well by double clicking and it will just fill that in, or you can pull it all the way down again like we did in the other column if the double click isn't working. So we have wavelength in meters. So at this point now we're ready to use this equation to solve for S. So the first thing I would do is say, okay, we're going to need this term here, which is A divided by wavelength to the 5th. Right, so we know this is A, so we will do equals to this value, and we want to keep that fixed. So F4 again, divided by the wavelength in meters to the 5th power. So to do the 5th power, you do the hat sign to the 5th. Okay, so we'll call this the first term, and we'll call this the second term. Let's try this. Do the exponent first. XP. Okay, so on this one, what we're going to do is just this term right here, which is going to be equal to exp, means e to the power of whatever you put in the brackets, and so this is going to be b divided by the wavelength. So we'll come back over to here, equal to b, and again, we want that is fixed, so F4 divided by the wavelength here, and that we want to keep relative, so as we pull that down, the wavelength will always be changing because we've left it without the dollar sign. Okay, so what we have now is that term and this term, so we're going to, let's put together this second term by saying this is equal to 1, this one, divided by bracket this term minus 1. Okay, and so then we have the final, the S, which is the total equation, which is just going to be equal to the first term times the second term. Okay, and so what we want to do is now pull all 4 of these down, or double click if that works for you, to 1,000. Such. And so what we have then is we've solved S for all the range of wavelengths at a given t. So let's shrink everything down here so we see it a little better. Okay, so what you want to plot then is your S as a function of wavelength, and we can just use nanometers. scatter plot like this, and we will finish it. So that is what your Blackbody curve looks like at temperature of 1 times 10 to the 4th. So now you can play with this by looking at how the wavelength changes as we change temperature. So if we change temperature to the value of the sun, roughly 7,500 or something close to that, you can see the peak has shifted. If we change temperature to say 1500, you can see it's shifted much further and gotten broader. And if we look at something like the temperature of the Earth, which is close to 300, we can see it's shifted much more. So you can see that at this point the peak is now towards the limit of our wavelength in nanometers, and we cannot solve that by just continuing to pull down. We can go as far as we would like in range. So we can pull that down another 1,000 if we like. Like so. Come back up and replot our graph. So it's not encompassing that. So we can say what is S as a function of wavelength. And so now where we had stopped here before, we're now way out to here, so we can see our lambda max. So how to figure out lambda max is now just to find the biggest number. So you can do this visually if you'd like. So we see we're at 10 to the minus 12, 10 to the minus 11. Whoops. So 10 to the minus 11 range, 10 to the minus 10, so getting bigger, 10 to the minus 9. So what you're looking for is the biggest number. So now we're back to 10, so it's somewhere in 10 to the minus 9th. So what we're looking for is the biggest number. We can see that significant digits is giving us a problem, so we can format number, increase the significant figures. Whoops. Format cells, number, I want scientific with 4 decimal places. Okay, so 10 to the minus 9th, here we see these numbers are bigger than these numbers, so 1.11 versus 1.10, so we will go up. So it's increasing, 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 70s, 80s, 90s to 1.2. Continue now, we're starting to go back down, so we see our peak is going to be somewhere around 1.2, 144 times 10 to the minus 9th. So if we wanted, we could expand that a little bit more, go out a few more decimal points, and see that there's quite a few similar wavelengths, but in the end 1.44 times 10 to the 33 is the biggest number. So that is our lambda max at 300 degrees Kelvin. And you can find your other lambda maxes just by changing T and looking for the biggest number in that column. And that should help you.